Man, that's a lot of thrust. Well, so far we've talked about weight, lift, drag. So of the four forces of flight, that leaves thrust. And today we're going to discuss how we generate thrust, why we need thrust, and why engines are hung on an airplane the way they are. So why do we need thrust? Well, it stands to reason that to propel an airplane through the air and get the air moving over the wing to generate that lift, we got to have some means to do it. There are two common means of developing thrust on a powered airplane: propellers and jets. It shouldn't come as a shock to learn that they both involve Newton's second law. Remember the rate of change of momentum, F equals ma, and how we developed lift and drag from this relationship? Well, thrust works on the same principle, except instead of working vertically, as in the case of lift, it works horizontally, as in the case of drag. Equal and opposite again, huh? So let's look at how the rate of change of momentum is generated to yield thrust. Consider an airplane with a propeller. As you can see by this section, a propeller is actually an airfoil very similar to that of a wing. And like a wing, it creates a rate of change of momentum as the air flows over it. To get the air flowing over it, the engine turns the propeller through the air, which results in a rate of change of momentum that we call thrust. To look at the factors that affect thrust, let's go back to the F equals ma equation. If I want to keep the thrust the same, I can use a large amount of air mass and accelerate it just a little, or I can use a small air mass and accelerate it a lot. It's like folding a piece of paper into a fan to cool yourself off in the summertime. If I have a small fan, I have to move it very fast to get enough airflow over me to cool me off. Whereas if I have a bigger fan, no, I don't think so. A bigger fan, I can move it much slower to get the same amount of airflow and get the same cooling. Well, the same thing applies to a propeller. I can use a large diameter propeller, which brings in a large air mass, because it covers a larger area. So for the same amount of thrust, I don't have to accelerate the mass as fast. With a small diameter propeller, there's less mass. So to keep the rate of change of momentum the same, the prop must make the air move faster and cause a greater change of velocity. To prove this works, let's rewrite the F equals ma equation. We know the mass is equal to the density times the volume, so the second law can be expressed as F is equal to rho v times A. As the case with wings, the volume is the number of air balls which pass through the propeller disc at any given time. Simply stated, the volume is the area of the circle the propeller makes as it turns, times a single unit of air. Since the area of a circle is pi d squared over 4, the thrust equation is now F is equal to rho times the quantity pi d squared over 4 times A. This leaves us to deal with the acceleration. It can be proven that the acceleration is equal to the initial velocity of the air just in front of the propeller times a change in velocity just behind the prop plus the change in velocity squared, all multiplied by 2. In other words, both the aircraft's speed, v, and how much the speed of the air mass has changed as it passes through the propeller, delta v, influence the acceleration of the air mass. And how much that velocity change occurs through the propeller is influenced by how fast the propeller is turning, just like when I used my fan. The change in velocity, delta v, can be expressed as a propeller constant, k, times the propeller RPM. Inserting this into the F equals ma equation gives us an expression that's really ugly, but if you stay with me, I promise together we'll get through it. Rewriting, we have F is equal to density times pi d squared over 4 times 2 times the quantity v times k times the RPM plus k times the RPM, that quantity squared. This can be rearranged to show the relationship between the airspeed, propeller size, and RPM. Well, we made it through the description okay. What do you say we use this Cherokee, try and tie all this together through an example? To fly at 120 knots, or 203 feet per second, where the air density is 0.0022 slugs per cubic foot, this airplane needs 241 pounds of thrust. If I install a 5-foot diameter propeller with a K value of 0.0044, how fast do I need to turn it to create enough thrust? Solving the equation, you should come up with an answer of the RPM equal to 3,000. Now let's change the propeller to a 6-foot diameter. To generate the same amount of thrust, how fast do we have to turn this propeller? Using the same equation, the RPM equals 2,155. This shows that by increasing the size of the propeller by 20%, we can decrease the number of RPM by 28%, and that saves a lot of wear and tear on the engine. To sum it up, prop-driven aircraft accelerate the air by mechanically pushing it toward the rear. There are practical limits, however, on how big you can make a propeller. For instance, suppose I wanted to increase the size of this one by 2 feet and add a foot to each end. Well, if this is 1 foot, what's wrong with this picture? You're right, it had hit the ground. We come down to the jet engine shop at the National Test Pilot School to talk about the differences between props and jets. Now, as we explained, the prop takes a large area of air and mechanically accelerates it to generate thrust. On the other hand, as you can see by the intake area of this jet engine, it's relatively small. So how do we get so much thrust? Well, we take the air that enters in the inlet area and compress it. And as you can see, each one of these sections has a smaller and smaller area between the blades. By the time it reaches this point, it's pretty densely packed. It enters the combustion chamber where fuel is sprayed into it, and that air-fuel mixture is ignited. That ignited air comes out the back at a tremendous velocity, almost explosive, and accelerating the air to a very high velocity. So what do we care about how high the velocity of the escaping air is? Well, let's talk about that with the use of a balloon. As you can see, if we take the balloon and pinch off the stem, the air inside is equal in all directions, so the net force is 0. But if I release the stem, there's going to be a net force at the very end, which will be unopposed at the forward end. That'll cause the balloon to fly away, just like that. The same thing happens inside a jet or rocket engine. The burning gases create high pressures everywhere, but they're allowed to escape only out the back of the engine. Sometimes, to get an extra kick, raw gas is squirted into the hot jet exhaust. This raw fuel ignites, generating an even higher velocity at the exhaust. We call these afterburners, or burners for short. That's what you see creating the flame at the exhaust of most fighters on takeoff. Although this kick increases the engine's thrust by up to 35%, burners use twice as much fuel, so we tend to limit their use. Most modern commercial engines are actually a combination of both a jet and a type of fan. This is the GE90. Produces 90,000 pounds of thrust. It does that through a combination of this core jet, which produces quite a bit of thrust to the rear, but the big part's in the front. That core jet turns these massive fan blades, which takes a large volume of air and accelerates it towards the rear of the airplane. That really aids in the thrust. So whether you're talking about a jet or a propeller, accelerating air to the rear of the aircraft is how you get airborne. And speaking of getting airborne, takeoff's scheduled for next session. See you then.